Good morning, everybody. My name is Suan.
My name is Tianyi.
And my name is Ryan. And the three of us are seniors doing our MQP at Worcester Polytechnic Institute, or WPI. And our MQP is building an off-grid solar inverter. So the purpose of this inverter is to take a 12-volt DC battery voltage and turn it into mains voltage, or 120 volts AC, that can power a small electronic device like a laptop or a fan. So we'll go through our circuit a little bit and then show you it work.
To start off, this is our 12-volt lead acid battery, and this is the disconnect switch. And then you see these 5 input capacitors, which are each rated at 100 millifarad, and their function is to store energy so that they supply non-DC current while the battery supplies an average DC current. Next up, we have the H-bridge, which converts 12-volt DC from the battery into a pulse width modulated signal, which approximates a sine wave, and it's consisting of 4 N-channel MOSFETs, which are controlled by 2 bootstrap gate drivers.
This is PI microcontroller, which can generate 4 PWM signals and then send them into the H-bridge. The 3-level PWM signal from the H-bridge is then fed through a step-up transformer, which produces 115 volt AC filter. This part is LC low-pass filter, which can convert 3-level PWM signals to a sine wave. The green one is filter inductor. Those two are filter capacitors. The output terminal block is then connected to a power strip, so the users can just plug their device such as TV or laptop into this power strip to charge it.
The last thing on our board here is a little feedback circuit. So what this consists of is a differential amplifier that actually steps the output voltage down from 115 or 120 volts to a 3.3 volt range. Then that's sensed by our microcontroller's analog to digital converter. And we do some math on the microcontroller to figure out how close the output voltage is to what we want it to be. And then we can adjust our PWM to keep the output voltage where it's meant to be.
So our first step is powering different loads. We first chose 220 ohm power resistor as our load because it matches the rating of filter. We use oscilloscope mass function channel 1 minus channel 2 to display the voltage across the power resistor. As you can see here, the output waveform is very sinusoidal. The THD is about 5%, which is very low, and the output voltage is stable at 115 volt.
After we successfully generated a sine wave over our power resistor right there, we wanted to see if our inverter could actually be used for a real household load. So what we've got here are 2 desktop fans, adding up to about 70 watts nominal. And so what we can see is that both of the fans are running, which is really great because our inverter works for something other than just a dummy load. But what we found is that the fans don't run as fast as they do when we run them off like mains on a real wall outlet. And the reason for that is because the fans are inductive loads and our filter is matched for a resistive load. And so you can see that as a result, on our oscilloscope over here, the waveform isn't as sinusoidal as it was. So a lot of the power isn't in the 60 hertz waveform that the fans want.
Our next load is a 60-watt laptop, and it does not have battery, so it's running on our inverter entirely. As you can see, because it's from China, we have to put an adapter to connect it to the power strip, but right now our adapter's not working, so we hooked it up with alligator clips. As you can see on the scope, it's a square wave and not a sinusoidal wave. This is because our laptop is an active load and our filter does not accommodate an active load. Thank you all for watching our short video of our project. We hope you enjoyed it.